I'm an intern, but I don't have to do those, which is why I love being an intern in the office.
Wait, what?
If you're an intern in the office, you don't have to do any of the assignments because you're a different type of intern. I really appreciate that, honestly. Oh no, he's already started this stuff. Miss Claire, I have a question for you on the corrections. So, number 12, I got everything except the inflection points. I had to use the calculator and I got a decimal, but he said exact answers.
No, I think he said use the calculator.
You could use the calculator?
Yeah, because I even wrote it down there.
Okay. It's like, there's no way I can solve this confusing way.
I think that's why he said you could use your calculator on the test specifically for that question.
And that's why we're working on it. I got one.
I'm just gonna say Lobital and roll with it.
What?
I didn't do Lobital, but I did get Infinity over. What did I get? Yeah, I got Infinity over Infinity.
I'm so happy to have your notebook. Is it too late for people to sign up for the college Costa Rica trip? Like, I think applications are due in October, but is it too late to quickly?
I don't think so.
Okay. Because I managed to talk one person out of the high school trip.
Yeah, I think that they're still asking for people, yeah.
Okay.
Contact, Allison.
Okay. Because I was talking to Jennifer, and she's like, yeah, I want to go to Costa Rica. And I was like, have you looked at the college one? And she said, college one? So I started telling her some of the stuff we're going to be doing. And she said, that sounds even better because I'm going into wildlife sciences. And I was like, girl. Because they, in addition to service, they're visiting high schools down there to learn about their education. Because they have, full year education. That's not study. You don't get out of spring break to go back to school.
True.
Yeah, tell her about it. I don't know when they're paying for the flight, so it might be pretty soon. She's really interested.
And then I was talking to Bree. I was trying to convince her to go on this Costa Rica trip, but she said the only concern was her medicine.
Yeah, I thought she was interested in it, to be honest.
She signed up for the one over there. Because she said something about how the professors over here aren't allowed to administer her medicine, and she was scared that that would be the same case for the.
She knows she's going with, science teachers that actually know what they're doing.
But are they allowed to give her medicine?
Oh, sure, yeah.
I'll let her know. I was trying to convince all these people, and they're just like, well, I've already signed up, and Miss Mallory's going to hate me if I back out now. I was like, okay.
Well, she came to the info session on Costa Rica for college.
I'm excited. I can't wait.
Okay, so for your inflection point,
Are you signed up for Home 180?
No, I have my meeting with Miss Holmes today, so I'm going to go ahead and do that, and then Sally has to come sign up for it.
So why are you not signing up for Calc 2?
I don't know. I still have to talk to Miss Holmes because apparently either my bio or chemistry lab bio is going to be at the same.
Yeah, but you don't need bio.
I need the second one for the AS degree.
Are you sure?
I need it to graduate next year.
Yeah, I know you, but I don't think you do.
I was told I had to take both, and that's why my schedule's going to be packed.
But I thought you were taking both chems.
I know.
Then you don't need both
You don't need
bios.
both bios? I was told I had to take both 1 and 2.
That's what
I was doing, because I'm taking Bio 111, and then next semester I'll do Bio 112, and then senior year I'll have a chemistry.
Did you take bio with Miss Mallory? Well, who told me that?
I mean, maybe you do, but I think you just need one sequence and then extra math and science.
I'll have to talk to Miss Holmes.
Okay, so for
But
your
I'll have to take humanities as a continuing ed class because I already took it last year. But Sally didn't have to take it. Okay.
Okay, so for your inflection point,
Yeah.
isn't the when it equals 0, when y equals 0? Like, I put that on my calculator and that's what I got too, but I thought it was when y equals 0, so I moved it over just a little bit.
It's
I had
zero.
that date. I got my data.
There's like, that would just be a.
I go out of
The inflection point is starting. So you have to plug the y value in, or this value into the original equation to get the actual inflection point of the root. When you solve it for, that's not an inflection point, that's a root. But the root tells you that there's an inflection point.
So, these are off.
Well, you have the right numbers, it's just the inflection point should be
They
part
even
of.
have, there's an inflection point.
What's going on? You doing all right? Oh.
Oh, that'll work.
I was texting Brittany last night, and I was like, hey, I finished number 6, and I wanted to make sure that you got something similar to me. And she was like, yeah, I haven't done it yet. I was like, Brittany, you've got to do it, because it's due on Monday. And she's like, yeah, I don't know if I'll tell you. I was like, fine. I think we're at the point where we're all losing motivation in this class, which is not good.
True story.
Especially when I have to graduate after next semester and I don't have time to fail stuff. This class would be really fun if it didn't have grades. Like if I wasn't failing tests and stuff, I would legitimately enjoy this class. I like the material. Where's everyone else?
Good morning, everyone. Just before we get started, you have your test rework. You can you have your test rework that you turned in, hopefully, as corrections. And I've gone ahead and put some notes on here for the next section. I don't know how well you can read that on the video monitor, but we'll go over real quickly. So in section 5, we're doing related rates. The basic premise of what we're going on is that if the two quantities, y and x, are related, then their rates of change will also be related. That makes sense. That will be achieved by implicit differentiation. If you differentiate this side, you get this. Differentiate with respect to t. So rate of change with respect to time. And then a quick review of some geometry that you have, I'm sure, seen before somewhere, some stage. Pythagorean theorem, similar triangles, those are obvious, easy. Area of the circle, excuse me, pi r squared. Volume of a sphere, not quite as obvious, but 1/3 pi r cubed. And then volume of a prism is defined to be so there's a whole bunch of different formulas out there, but I think it can be simplified if you think of a prism, by definition, is a three-dimensional object that has parallel and identical ends. Like that has a square end on one end and a square end on the other. If you have a three-dimensional object that looks like that with ends that are parallel and identical, that can be square. It could be, if I fold in one of these, I could make triangular prism, like on Dark Side of the Moon. You see that? Oh, well, there's a triangular prism. I can make, if I take out all the creases, I can make a circular. Take out all the creases, I get a circular prism. Point is, they're all very similar. And the volume of all of those, whether it's a circle or triangle, square, whatever, volume is simply the area of that parallel base. So if it happens to be a square, then find the area of that base, multiply it by the height, you got the volume of the object. If it happens to be triangular, find the area of the triangular base, multiply by the height, you've got the volume. If it happens to be circular, find the area of the circular base, multiply by the height, you've got the volume. It doesn't get much easier than that, I don't believe. Now, the only other thing is if it's a cone or a pyramid, meaning you start with a prism and pinch the top to a point, which I don't want to mess this up yet. So, if you pinch it to a point, what happens is the sides now lean in. And when they do, you lose a good bit of volume. And in fact, you lose 2/3 of the original volume. So the volume of a cone or a pyramid looks the same. It has the area of the base, so area of the base. So if you happen to have a square pyramid, the bottom is a square coming to a point. You find the area of that square base, multiply by the height, but then take 1/3 of it because you pinched in the top to a point. So 1/3 of the area of the base times height. That's same for a circular. If you have a cone, circular base, the height, and then 1/3 of it, the volume of a cone. So these two formulas go together. One's for a prism that has parallel ends that are identical. One's for a cone that has one end being a shape and then the other end being a point.
Can we see the board one more time?
Now let's get back on the board there for a moment. I want a moment to look at that, and then we'll do some examples. We're good now? Okay, so we'll start with a fairly simple example right here. Let's say, kind of a classic example of this is you drop a pebble. My pen is not working. So if I drop a pebble in a pond, it forms concentric ripples. Its radius grows at, let's say, 2 feet per second. Find the growth rate of the area of the circle. Okay. The radius is 5 feet. So that's a kind of a typical type of problem, as it is an introductory, fairly simple problem. Fairly easy to visualize what's happening. So you drop a pebble in a pond, and you get a circle that forms. Actually, several circles form there, and they grow outwards. Well, let's just focus on the outermost one. So it tells me that, I need to use color here. Radius of this circle is growing I'm going to use a rate of change for that. The radius grows, right here, the radius grows at 2 feet per second. So that means that the change in my radius per time is 2, keeping in mind the unit of measurement. I'll even put it on there with that, 2 feet per second. Okay, so that's what's given. This is given. What does it ask us to find? Find the growth rate of the area. So it says to find the growth rate of the area. That's all it says. When the radius is 5 feet. So this 5 feet is important right here. That means we're going to evaluate this rate of change in R equals 5 feet. So I'm given one rate of change. I want to find the related rate of change at a particular point in time. At some point in time, the radius will be 5 feet. At that point in time, I want to know how fast the area is changing. Everyone follow the diagnosis of the problem. We haven't solved it. This is just interpreting the English into some calculus symbols. Now I'm going to do the work. So based on the theory we started with, to find two related rates, you have to have a related quantity. So what's the relation between R and A for a circle? Yeah. So we'll write an equation. Area equals pi times R squared. So that's our relation of quantity. That was fairly simple. Agree with that? I have a relation of two quantities. I have an area related to a radius. That's good. I want to relate from that the change of radius and the rate of change of area. I must therefore take the derivative of this equation with respect to time. So I'm going to do the derivative with respect to time of A, and the derivative with respect to time of pi r squared. So, what is the derivative of area with respect to time? ADT, we're trying to find. That's a good thing. Okay, on the right-hand side, I have pi as a constant. So I can just pull that pi off as a constant multiple. But now r is a variable. So how do I do the derivative of r squared with respect to t? Not with respect to r, but with respect to t. That's going to involve implicit differentiation. Remember when we did derivative of y with respect to x, you had like y squared, you had to do 2. Do you remember doing this? Derivative with respect to x of y cubed was 3y squared times dy by dx. Y'all remember this? This is differentiation. Same thing right here. So the derivative of r squared with respect to t is 2r times dr by dt. Same thing, it's implicit differentiation. So this, all we're doing is implicit differentiation. Done before. Almost done. What are we trying to find? The ADT. So I go back to my equation and I isolate that variable on one side. Okay, done. If it wasn't, like if just pretend for a moment. Pretend I was asking you to find dRdt. Then you would solve for dRdt. It's not that hard. But this one's already done, so it's a fairly simple problem. The ADT was what I'm trying to find. It's already isolated. So all I have to do now is plug in the information I know. Okay, so we're trying to find the ADT evaluated at r equals 5. Well, according to what we have here, we have a pi times 2 times r. Well, it says right here that r is 5. So we'll plug a 5 in. And it has a dRdt out here on the end. What's dRdt? So right there is 2. That's 2 feet per second. That was 5 feet. And so it looks to me like we get an answer of 4 times 5 is 20. So we'll say that it's 20 times pi feet squared per second. Questions on that? Any questions? Would feel good about that one? It's pretty simple. I don't all stay quite that simple, but that's the idea. Okay. Suppose we are building a sand castle. So we're getting sand and we're dumping it. We're not really trying to pack it together, we just dump it. When you dump sand or any kind of granular material, it spreads out into a cone shape. Just natural, that's what it do. And so depending on the friction of the molecule of the grains, how wide, how tall it is. But let's suppose we're dumping sand onto a pile. Forms a cone. Whose height always half the diameter. So it tends to spread out so that it's wider than it is taller. And that ratio is not constant. That depends on, again, the type of material. But so I'm just making up a problem. Now, so that's just giving you some visual image of what's happening. I guess I could go ahead and draw a picture of that just to make sure we're clear in the way of the rest of the problem. So I've got some kind of cone-shaped object here. And it tells me that this height, so the height from the base of the cone to the top of the cone, there's H. And then there's my diameter all the way across the bottom of the cone. That's my diameter. And it tells me right here that the height is always half the diameter. Height is always 1/2 diameter. Okay. That's not even a complete problem. That's just analyzing the shape, the geometry, what's given in the geometry. Okay, so if we're dumping sand at about 2 cubic feet per minute. Find the rate of change of the height when we've dumped 30 cubic feet. Okay, so trying to match up the colors. What's given in terms of rates of change? Going to find our given rates of change. What's our given rate of change? Okay, so that's given. What symbol should I use? What rate symbol should I use to represent that number? So something is equal to 2 cubic feet per minute. What symbol should go there? Change in volume per time. So that should be dV dt. Okay, I'll answer that. What else to find? Rate of change of height. So find change in height. So find change in height per time. But that's not all that was given, that was asked for. Rate of change of the height of the pile depends on at what point in time we're talking about. So what point in time are we talking about? So we find this when volume equals 30. Understand? Questions so far? So once again, I'm taking it kind of in steps. I'm taking the basic words, figure out what the shape of the object is. Then I'm looking for my rates of change information, what's given and what I'm trying to find. And now comes the, quote, hard part. That's writing an equation. Volume of a cone. What did we just discuss about volume of a cone? Volume of a cone, 1/3 area of the base times the height. Okay, so volume equals, how do you calculate the area of the base? Since it's conical, that means circular, then it's going to be pi r squared, that's right. The volume of a cone. We're doing pretty good so far. Any questions on that? And 1/3 of area of the base times height for any kind of pointed shape like a cone or a pyramid. This happens to be a cone, so it's a circular base, so pi r squared. But here's my next question. We're dealing with dv dt and dh dt. Those are our two rates of change we're dealing with. How many variables do you see in your equation here? 3. V and h, which are good, but then we have r, which is not good, because we don't want r because we're dealing with h and v only. But Justin said, wait a minute, somebody pointed out, what am I taking into account? H is equal to 1/2 v, so since h is equal to 1/2 v, then h must be equal to, what's 1/2 of v, folks? Oh, r. So volume equals 1/3 pi times h squared times h, which is 1/3 pi h cubed. So now we have two variables, v and h, and those are the two that we wanted to relate, v and h, because those are the rates of change we wanted to relate. Everyone with me there? What do we do next? And do the derivative, implicit differentiation, that's right. So, the derivative of v is dv dt. Now I got to take the derivative of 1/3 pi h cubed. What do we get? Derivative of that right there. We're getting h squared times pi times dh dt. Everyone see this? And 1/3 and the pi are constants. Okay, so we'll just copy those down. Now you're going to take the derivative of h cubed. How do you take the derivative of h cubed? I can't hear you. I'll speak up. Implicit differentiation, which is going to give me 3h squared times dh dt. Now it looks like the 3's cancel. So I end up with dv dt I times h squared times dh dt. That was pretty easy. And I'm not done yet, but I'm getting close. Again, the process is analyze the words, come up with a picture that works with it, identify the rates of change you're trying to match up, and then write an equation and get it down to the two variables you're dealing with. And once you do, then you differentiate. Okay, you just have to remember implicit differentiation. I need to go over the side work some time. Okay, so over here, we'll finish the problem. I have dv dt, so I'll just copy that. Rate change of volume equals pi times h squared times dHdt. What are we trying to find again? We need to solve for dHdt because that's what we're trying to find. So that means dHdt is equal to dV divided by pi times h squared. So far, so good. I'm trying to find dHdt evaluated at, so I'm trying to find, according to the find, dHdt evaluated at V equals 30. So I start filling in the pieces of the puzzle. I'm given the rate of change of volume is 2 cubic feet per minute. So that's 2 cubic feet per minute in the numerator. And then I have a pi, which I can just write in there, and I have an h squared. So what do I put in for h? Are we with me?
Yes.
It's Monday morning. It's Monday morning. I got to put in a number for h right there that says h. But I'm evaluating at v equals 30. So I'm not putting 30 there because 30 is a v. 30 is not an h. But is there a relationship between v and h? Okay. Way back over here, we saw that volume. Not quite that far over. It's Monday morning.
It's a little sensitive.
Yeah, a little sensitive one. Volume is 1/3 of pi h cubed. Volume is equal to, so we saw over there, volume is equal to 1/3 pi h cubed. Well, I ought to be able to find out what h is from that. Right? If I put in a 30 cubic feet here, then h cubed is going to be 90 over pi, and h is the cube root of 90 over pi. So we'll put the cube root 90 over pi. It's going to be, I guess that's feet. Yeah, because h, this was cubic feet, and then I took the cube roots, that's in feet. Okay, so now we'll let you just approximate, I guess. Yeah. Decimal approximation. Number? 3.05. Anybody else get that number?
I know it's 3.06 if you round.
3.05. Anybody else get that number?
I got if you rounded it would be 3.06.
Okay, well, we'll go 3.06. Sounds good. And that would be in feet per minute. Okay, so one more time in quick review. This was dealing with a cone. I have a volume for a cone formula. I was given a rate of change of volume, and I needed to find the rate of change of height. And it took writing an equation, taking the derivative. Oh,
Just,
as you go all the way to the, I want the final answer. I got your calculator out. You don't need to do it in pieces. Just put the whole thing in at once and be done with it.
I got 0.068.
So 0.06 like that?
Yeah. We can round it.
I want to use a calculator.
sorry, Josh.
We're all in agreement with 0.07 now.
Yes.
Okay, good. That makes more sense than 3 feet per minute. That's a lot of sand. If it's growing in height by 3 feet per minute, that's pretty fast. That's a lot of sand coming down. So, especially considering that it spreads out as the pile grows, it gets much wider. Okay, let's try another classic problem of some sort. Try another one with a cone. So you have a storage tank. That's an inverted cone. Let's see, whose top is 10 feet diameter and is 15 feet tall. Find the loss rate of water and the depth is feet. If depth at have a storage tank that's inverted cone, so the point is out down, and water's draining out the bottom of the cone, and the depth is dropping. You're sort of watching like a little meter on the side of the cone. You see the water going down 2 feet a minute, and you want to know how fast am I losing water? Okay, so what do we got? Cone. The distance across the top was given as 10 feet. No. The height was given as 15 feet. What were we given as our given rate of change? Okay, so let's call depth, what we're going to say is that the depth is going to be the height of the water. So we've got some water in here, partially filling the tank. It's been dropping some. So this depth of water, we'll call it H for the amount of water we have. So we'll call that DHDT. And what number do I assign DHDT? Almost. Think about it a little more. What's happening to the height, the depth of the water? You're losing value, right? So the rate of change needs to be negative. So the depth is changing at negative 2 feet per minute. What are we asked to find? So loss rate of water. What do you think that, right here, loss rate of water? What do you think that's asking you to find? The volume you're losing, that's right. So find the volume you're losing. When do you want to find it? When the depth is 6 feet. So when H equals 6. On this? Well, apparently I need to relate volume and height again. Well, okay, let's do that. Volume of a cone. Volume of a cone is 1/3 IR squared H. In fact, I'm going to put the green H in there to emphasize that I'm talking about the height of the water. Because this is talking about the volume. V is talking about the volume of water, not the volume of the cone, the entire cone, not the entire tank, just the volume of the water that's in there. That's why I drew the water line right here. So to get it down to just a V and an H, I got to replace an R in here like we did before. But this time I didn't give you the same relationship. Before I told you height was half of the diameter. That's not true this time. But I'm giving you some information in the geometry of the problem to relate H and R. R squared is 10. Oh, no, that's not going to be quite right either. The R that's up here, this R, so let me get another color. This R here is the R of the water itself. So right there is R. I need to know the radius of the water. Exactly. Cones, like triangles, are similar. The radius of this water cone, in proportion to its height, is the same as the radius of the big cone in proportion to its height. We can make a relationship right there. We have that R over height of water radius of the big cone, which is 5, over height of the big cone, which is 15. That must mean that R is equal to 1/3 of H. All that? So this is just based on the idea of similar triangles right here. Push down. I can now replace R, 1/3 of H, I have volume is equal to 1/27th pi h cubed. Got down an equation that's relating volume and height are related, and those are the two I wanted to relate because those are the two rates that I want to relate. Now I have to find the rates by differentiating. So derivative of v is dv dt. On this side, the 1/27th pi is a constant, and then you get 3h squared dh dt. And once again, the 3's cancels with the 27, so I get 1/9 pi h squared dh dt. So that's the relation between change in volume and change in height. So all I have to do is it says to find, right here, find dv dt evaluated at height equals 6. This one's actually easier because I'm directly finding by plugging in a 6. Last time we had to back calculate what was needed. This time I'm just directly plugging in a 6 for height. So this becomes 1/9 pi times 6 squared times dh dt was -2 feet per minute. So that's equal to -36 pi feet cubed per minute. Volume is changing at -36 pi. Did you expect anything?
You should have something to
Hold
do.
on. Question.
It's
Question.
1/9.
Yeah, shouldn't it be 1/9 instead of 1/2? So it's negative.
Well, no wonder.
8.
Thanks. 1/9. That's a good catch. So 1/9 doesn't. That one's right. You're right. So 9 goes into 36. Yeah, you're right. So that's -8 pi. Good catch. Thank you. I just like to change a 9 to a 2 just to see if you guys pay attention. It's a random thing that I do once in a while.
Celebrate me.
Okay. Any questions on that one?
It's not like one of those cups you drink at offices. Those little-
Let's do another example. And another classic example.
When's this test? Tomorrow or Wednesday?
I'm going to erase this one. We've had time.
Dude, I shaved for the first time in like a month. It's crazy. I feel like a baby. I look like 2 years older. It's weird.
So let's see. This is the one I first introduced when I first started talking about this block material. One of the classic cases or examples that you see in calculus books all the time. A ladder leans against and let's give it a length, a 20-foot ladder leans against the wall. And starts to slide down the wall. Let's say it slides down the wall at 3 feet per second. Find the bottom slipping away from the wall. When bottom is 5 again.
We have to evaluate that.
Question was, if you didn't hear it, Davidson, will on these problems always have a specific point in time when you're evaluating? The answer is yes. Generally, we don't say at 3 minutes, though you could, but you are usually relating it to one of the variables you're dealing with. Again, you'll always have a specific point in time. Okay, so geometry is something like this. 20 feet.
Triangle.
All this X, let's call that Y. We are given, what are we given here? Slides down the wall at 3 feet per second, so that means that dy dt, y is changing. How's y changing? Y is getting shorter, so that must mean the rate is negative 3 feet per second. We're to find how fast it's slipping away. So the xdt when x is 5. That's fairly easy. Okay, so what's the equation that relates x and y? That's the two rates of change I need. So I need an equation that relates those two variables. There's here. Squared plus y squared equals 20 squared.
Why is that? Is that Pythagorean?
Yes.
Pythagorean theorem. So then we'll take the derivative with respect to time.
Oh, wonderful.
The first derivative, this one over here. X dx dt plus 2y dy dt. 0. Which one are we trying to solve for? The x dt. So we'll solve for that. The x dt equals negative 2y dy dt over 2x, which is negative y times dy dt over x. So I can evaluate now. I have to find dx dt evaluated when x is 5.
Oh my gosh, I think I understand. Oh shoot.
So I have this is equal to negative of y times dy dt. Dy dt is negative 3 feet per second. And then divided by x, x is 5 feet. So the only thing I'm missing out of my computation is whatever y is. All right, in terms of what? Go back up here. If x is 5, then you ought to be able to find y. So apparently, I squared plus y squared has to equal 20 squared. So maybe y is equal to the square root of y squared minus 5 squared. That is 400 minus 25 is y equals the square root of 375. 375. It's the number for that. What measure will that be in?
What did he say?
Yeah, it should be feet per second because we're talking about dx/t, but also if you keep up with your units of measure in here, like this feet and that feet cancel, so I'm just left with feet per second all the way through it. Keep up with the units of measure, you'll get the right unit of measure. Okay, that was a classic example, not too bad. Let's try. Any questions on that one? I don't know, what are the numbers of that?
You would have to find.
25, that has a 25 that goes into it. What is that? 25 times 15? 5 root 15? So the 5's cancel, so this must be 3 root 15 feet per second, I think. Okay. How much time we have? Let's see if I can give you another problem that y'all work on from that. Oh yeah, we got 15 minutes. You can work on a problem. Okay, so here's your problem. So a watering trough, paddle or something, is a triangular prism. Ends are isosceles triangles. Let's see. What should be? 3 feet on the top. And, 5 feet. Water is pumped in at, oh, we need something else. One more piece of information. Let's say 5 foot long watering trough. Water's pumped in at 2 cubic feet per minute. Find the rate of change of depth. When depth is so help. I'll let you work on this for a few minutes yourself. Help get you started so you have a visual. So we have a prism, wide but not very tall. So it's 1.5 feet tall, is 3 feet across here. It goes back into the board, which I'm going to attempt to draw with a different color, maybe. Like that. I don't know if you can make that out, but the front face of it is a triangle, and it's isosceles, so that means this side is equal to that side. It goes back into the board, and the distance going back into the board is 5 feet. So this length here 5 feet. You have water being pumped into it. You want to find out how the depth is changed. So when we're saying when the depth gets to here, here's your depth, height. When it gets to there, that's the question. Want to visualize this? I need to make a depth draw. Okay, so we're going to work on it for a couple minutes, and we'll touch base here.
Brilliant. Is 1.5 the length of one of those triangle sides? Or is it like the height of the whole triangle?
It's the length of that side.
Okay. Do you like your phone?
What?
Do you like your phone? Your phone. Do you like it?
I just don't like how it doesn't light up on the station.
Let's see if my phone does.
Okay, so hopefully you were able to at least get your basic equation. Let's go through it real quickly, since we're right out of time. You're trying to find dB/dt, given dB/dt, find the HDT. Volume of a prism, we talked about earlier, is area of the base times the overall height. So area of the base times 5 feet, so 5 feet length this way. Area of that triangular base is 1/2 base times height. So here's my base, here's my height. And then I need only 2 variables, B and H, so I have to get rid of B. So I set up similar triangles and solve for B. And then simplify, and then I just have to take the derivative using implicit differentiation, then solve, after that, solve for dHdt and plug in, and I'm done. I get 0.2, which is the same as 1/5 feet per minute. Okay, so for homework, work on some problems in section 3.5, and tomorrow we'll wrap up. I'm actually 2 minutes early. What? I like people to, when I'm driving to work, to still have just, sometimes I just want to go up now instead of before.
Related factors, and what was the other thing, the first thing that we did?
Optimization.
Is that it?
Have a test on Wednesday on these 2 sections. So all of you action on this and any other review questions. Homework in section 3.5. Practice on.
I've been putting my notebook in my binder, but it's not working anymore, so now I have a notebook and a binder and a book.
You go, Chloe.
And at home, I got a book full of, I got a notebook that's just scratch paper, and it's like 4th of the way full.
Nice.
Huh? No, I haven't done it, I got proof, but
Let's not do until Thursday.
true story. So we don't have class tomorrow except for this.
Oh, no, not the assignment. I forgot.
Wait, what assignment?
You gotta give specific textual examples, but it's John Mellon, it won't be that.
I got 6 out of 10. I've got